A B-tree is the backbone of database indexing. It keeps data sorted, supports fast lookups, and stays balanced automatically. Today we'll build a full B-tree from scratch in Java, insertion with node splits, search, range queries, and in-order traversal. This is the data structure behind countless production databases. The class is generic over any comparable key type. The parameter t is the minimum degree. Every node, except root, must have between t1 and 2 t1 keys. The constructor creates an empty tree with a single leaf root. A node holds a list of keys and a list of child pointers. N tracks the current number of keys. The constructor pre-allocates capacity for 2 t1 keys and 2 t children, one more child than keys. Find key index performs a linear search to locate where a key lives or would be inserted. Insert first checks if the root is full. If so, it creates a new empty root, non-leaf, and attaches the old root as its first child. Then it splits that child and only after that inserts the key into the now non-full root. If the root is not full, it simply inserts into it. These public methods delegate to private recursive helpers. Search returns true if the key is found. Range query collects keys between low and high, inclusive. Traverse prints all keys in order with indentation to show the tree structure. When a child is full, has 2 t1 keys, we split it. The median key, at index t1, moves up to the parent. The right half of keys, and children, if internal, are moved to a new sibling. The original child keeps the left half. Then the parent inserts the median key and the new child pointer. If the node is a leaf, we insert the key at the correct sorted position, ignoring duplicates. If internal, we find the child to descend to. If that child is full, we split it first. Then we recursively insert into the appropriate child. This guarantees that we never traverse into a full node. Search walks down the tree. It finds the first key not less than the search key. If equal, the key is found. If we reach a leaf without finding it, the key does not exist. Otherwise, it recurses into the appropriate child. To collect keys in a range, we find the first index where keys might be greater than or equal to low. For each key that is less than or equal to high, we first recurse into its left child, if internal, then add the key, and move right. After the loop, we recurse into the final right child. This efficiently grabs all qualifying keys. Traversal prints keys in sorted order. For each key, it first visits the left child, if internal, prints the key with indentation proportional to depth, and finally visits the rightmost child. This gives a visual representation of the tree structure. We create a B-tree with minimum degree 3. Then we insert 20 numbers in random order, print the balanced tree, test search, run a range query, and insert 5 more keys. The traversal output demonstrates how keys remain sorted and the tree stays balanced. The in-order traversal prints keys from 1 to 20 sorted. Search works, range query returns the expected sublist. After inserting more keys, the tree rebalances without any manual intervention. You've built a fully functional B-tree from scratch. It stays balanced through splits, supports efficient searches and range scans, and is the fundamental data structure behind database indexes. Now you can adapt it for on-disk storage or use it as a sorted dictionary in memory.